Axel Pries is going to talk about modeling of adaptive processes.
Thank you very much, and thank the organizers for the invitation to this really brilliant meeting. I will talk a little bit about the problems which nature has in dealing with adaptation. And most of what you have in an organ, in a whole body, in any system is a result of adaptation. And if you look to the vascular system, for instance, you see very different patterns in different organs, and they have to be adjusted in topology and morphology to achieve adequate function. And that's not a simple task. And one problem in that is that you don't have a blueprint to compare it with, and there's no one looking at the end result comparing it with any blueprint. And what we think is the mechanism, or that's just a term for it, is angioadaptation, which includes adjustment of vessel number and structure, and could be alternatively phrased as vascular plasticity. I fear that I will not fulfill what Sasha was alluding to, what I would talk about, but it's included to some degree or another. In this adaptive systems, you have a kind of a feedback loop. There are certain conditions, like in the vascular system, shear stress or PO2 or SO2, and in these conditions are crucial for vascular or organ function. So the distributions of these things must be adequate, and they must be robust. If you consider what Dennis Noble said yesterday, these systems have to be able to withstand some shaking and still come back to the more or less adequate situation. You cannot have an unstable equilibrium here. They must be really robust. And that's done by creating some stimuli based on these conditions in a steady state that might be zero, but maybe it's even fluctuating. And that's creating a biological reaction. And in this biological reaction, you have to envisage some kinds of reaction rules. So each player, like these agents, has a set of rules and is responding to the stimuli. And these rules are identical for each element in the play, like each vessel. And the outcome is just a reaction of the different stimuli given to a given vessel. Because if you a priori say an artery has a different reaction from a vein, then you are again imposing a blueprint, and you are not allowed to do that. The vessel has to find out for itself whether it is an artery or a vein, at least in the beginning. In the end, it may be finally determined, but not in the beginning. So then the structural features come out of it, and as I said, there are no limits to it, so it can go awfully wrong, and there are no blueprints. And when I remind my medical teaching, I was always a bit worried about pharmacotherapy, because why are we more clever than nature is? If we need more, let's say, anti-inflammatory or more VEGF, why don't we do it? But the only reason to allow us to do that is that we can look on top of the organ and say, okay, we have an idea of a blueprint in our mind, and sometimes nature cannot do it based on the local signals, but we can do it based on the global evaluation of the state. So that might be at the very heart of any medical therapy, opposing this idea of self-healing, which is also around, obviously. So this is then used for the adaptation of vessels, in this case for the structural or diameter adaptation. So we have a number of stimuli like shear stress, transmural pressure, metabolic stimuli, and very important conduction of information along the vessel, and that can be put together into a relatively simple module describing vascular diameter change and wall mass change in response to the stimuli. And we found that this kind of setting allows to generate or maintain structural distributions which are very similar to what we see in vivo, what we measure in vivo, and they are reasonably robust. And here you see, for instance, in the capillary network in the mesentery, the PO2 distribution and the shear stress distribution. So this is the general approach, and now I will want to give one example relating to the heart, since this meeting is devoted to the cardiac physiome. So the question is of myocardial heterogeneity, and Jim is obviously a pioneer in this problem, so many of these ideas come from his earlier talks and publications. So the local perfusion in the heart exhibits a significant stable heterogeneity, and it turns out that this is correlated also to a local metabolic heterogeneity. And Jim said what is still unproven but nevertheless compelling is that local flows and oxygen consumption are driven by local needs for ATP, so the local metabolic rate is driving this kind of heterogeneity. And so I wanted to approach that from a slightly different angle and pose the question, is that really true, or could the opposite be true? So is flow adapted to a heterogeneity in demand? You see a heterogeneity in flow and in demand, but you don't know what is prior. Or does the vascular heterogeneity is there first and lead to a heterogeneity in demand? So I checked these, the second hypothesis, and I started with the process of vascular generation. And that's again something where you see the missing of a blueprint. So vascular systems are not designed on a drawing board and then put into place, but they have to be generated by local stimuli in a more or less stochastic or random process. And this process leaves its fingerprints in the end result. The end result is not an engineer's result, it's a biological result. And this is a fundamental difference, I think. So angiogenesis is a stochastic process, as we all know. We need to put vessels in place, and we take out 90% of these vessels and remain with something which is more or less adequate. And the other thing is a dimensional problem. If you want to perfuse a planar tissue, you don't use the third dimension to come in from both sides. So you have to put the vessels into the same dimensional space you use for the tissue. And that is a reason why you have long and short pathways. So there is a topological or dimensional problem, and the other thing is the heterogeneity in vascular generation. So we have two sources, maybe more, of heterogeneity, and there is an inevitable heterogeneity in vascular systems, which are completely different from an engineer's solution where you could have it all flat. And this leads to an heterogeneity in perfusion and an heterogeneity in oxygen supply, which is inevitable. Now the question is, can we deal with this? I said there is angioadaptation, so can angioadaptation take it out completely? Because if you have a bad system, put in a high feedback, let's think of amplifiers in the 80s. You have a bad amplifier and you put in a very high feedback loop, and then it's more or less good. So is that feasible? So can an angioadaptation abolish functional heterogeneity by adapting vessel diameters to local oxygen levels, decrease heterogeneity in perfusion, or adapt the oxygen demand and make the system more homogeneous? This is a possibility which we checked, and I will show you the data. The other thing is an adaptation of oxygen demand. Is that only beneficial to flatten the system, or is it increasing an additional heterogeneity? Because if you adapt local oxygen demand to local oxygen levels, that will lead to an additional adaptation of vessel diameter, increasing heterogeneity of perfusion. So you might be in a difficult situation where you cannot completely flatten the system, because what you do to flatten it creates another heterogeneity at another location. So very quickly, answers of our model based on the mesentery. When here we increase the metabolic sensitivity of diameter adaptation, and what you see is a division between the left part where we have a too low metabolic sensitivity and we get a very high heterogeneity of flow and oxygen, a very short path length, which means shunting of flow through very short pathways through the vessel. Through the network, and then this domain is more or less constant, with the only exception that the more you increase the sensitivity, the more you have to pay for it, but you don't get anything more. So above a certain threshold, heterogeneity is more or less flat, but it's not zero. So you cannot reduce it to zero, you can only reduce it to a certain level, and there it stays. And if you pay more, you don't get more. So heterogeneity cannot be reduced below a certain level. If you don't have this feedback, then everything gets awful, but above that it's not completely flat. The second thing is, if you play around with the sensitivity of adaptation of consumption, local consumption or local demand to local availability. So from here to here we increase the local response of demand to availability. And what you see is that by this you can increase the overall oxygen extraction. So you make the system overall a little bit more efficient, not very much, maybe 20% or so. And that is increasing heterogeneity. So when you say, okay, I have an inevitable heterogeneity in distribution, so here you have a region with a high flow and with a low flow. If you say both are using the same oxygen turnover, then you wasting the high flow which you have here. But if you adapt the local demand to the higher availability, you crank a little bit more net outcome out of net effectivity out of the system, but only to a certain degree. And if you drive it too hard, then the system becomes unstable. So in this region here, you can increase the overall oxygen extraction, but you also, by doing that, you make the rich people richer and the poor people poorer, and hoping the overall effectivity increases. That's going to a certain degree, but you know from the last year there is some limit to it. So the last question is, can this kind of model explain biological data? So is our hypothesis more or less plausible that the inevitable vascular heterogeneity drives the metabolic heterogeneity? It's very difficult to extrapolate, but you see that the simulation and experimental data at least show a similar relation of local demand to local blood flow, but that's not obviously a proof. It's just a kind of plausibility check. So the conclusion would be from here that architectural vascular heterogeneity, which is inevitable, generates heterogeneous distributions of perfusion. Angioadaptation can limit but not abolish this heterogeneity, and the additional adaptation of oxygen demand to heterogeneous oxygen availability can increase overall perfusion, overall function, but also increases heterogeneity of perfusion and demand. So the overall system in nature is not geared as creating the most homogeneous situation, but the most effective situation. And with this, I would like to thank my collaborators, certainly Tim in the room, and a number of other people in my lab. Thank you very much.
In tumor cells, it's sort of an example of great heterogeneity in angiogenesis, and even worse heterogeneity in oxygen delivery. It's as if it sort of fits in with your scheme, but wouldn't you expect this provocative angiogenesis to at least alleviate rather than make heterogeneity of oxygen delivery even worse?
Well, that's a very interesting question, and we worked on that for the last 6 years, and we just got the respective article published, but I couldn't sneak it in. What we think in the tumor is that the acceptable heterogeneity which you see in normal tissues, based on the kind of control mechanisms, is breaking down because the control mechanisms are reduced in effectivity. And what our suggestion would be that this conducted response, which is linking different areas together, is breaking down, and therefore heterogeneity goes to a higher level, which is then influencing function and therapeutic approaches and so on and so forth. And that's just published in PLOS Computational Biology.